Okay, let's get started. We are talking about gravitational wave detectors, and at the moment we are discussing the most relevant type of gravitational wave detectors, interferometers. So just to remind you of the basic idea, these are Michelson interferometers. So we have two mirrors, M1 and M2. Here a beam splitter, and here a detector, say D. Here's a laser beam coming in. And this arm length, let's call this D1, and let's call this D2. And then we have an interference pattern on the screen which depends on the difference between D1 and D2. And the formalism, the formula for this, I hope everybody remembers so the phase difference, this is the relevant quantity which you can read on the detector in terms of bright or dark fringes. The phase difference is given by 2 pi over lambda. Lambda is the wavelength of the laser which we are using, and then 2 times D2 minus D1. 2 times because the beam goes back and forth. So you see this is an instrument which transforms length, or length differences to be more precise, into a phase difference. And phase differences can be measured with very high accuracy. So lambda, typically for these gravitational wave detectors, they are using these Nd:YAG lasers which are operating at 1064 nanometers. So that's just outside of the visible spectrum in the infrared. And so here you should think of something like 10 to the 1,000 something nanometers, and then you can calculate what length differences you can measure if you know with which accuracy you can calculate phase differences. And what we want to calculate now together is the following: if a gravitational wave is doing us a favor, coming in perfectly orthogonal to this instrument, then it will produce a change in the difference of these two lengths, D1 and D2. So this quantity will change. This means this changes, and we can observe a change in the interference pattern. And we want to calculate really a quantitative expression for the phase difference to see on what quantities of the gravitational wave it depends. So, of course, I said this last time, the mirrors must be movable, of course, and that's one of the challenges for the experimentalists to suspend them in a way that they are as freely as possible movable in the horizontal direction, but not subject to any other kind of perturbation as far as possible. Okay, so we assume that a gravitational wave is coming in this direction. So we know it is transverse, so it will produce a change in length just in this plane. And we have calculated actually the pattern which is produced. You remember there were these plus modes and the cross modes. And let's assume that we have a pure plus mode for simplicity. So we calculated actually for the general case, for a plus mode and a cross mode, how the lengths, the length squared. Yeah, this is the distance. Remember, we had coordinates x in the beginning, and then we changed to coordinates y. The x's were attached to free particles. If the particle is moving, the x-coordinates doesn't reflect this. The x-coordinate is always attached to the particle, so it's fixed. Then we introduce these new coordinates y, which really gives the measured distance, the distance as it is measured with a metric. So you could measure this with the help of light rays, sending them back and forth, and this would be the distance from the origin of this freely falling particle, and it will depend on t in general. And this was given by the axis. And then the influence of the wave, was there a factor, 1/2 or something like that? No, I think it was just A plus. Yes, just A plus. The amplitude of the incoming wave. So we have a pure plus mode, so it's just A plus modulus. And then we have x1 squared minus x2 squared cosine omega t, and possibly a phase. Yeah, the A plus is in general complex, so it will produce a phase factor of this form. And then there was a second term with a cross mode, where you have, instead of this difference, you have 2x1 times x2. Yeah, this is the same thing, just rotated by 45 degrees. So this was the formula, and we want to evaluate this now for this situation. So mirror M1 has certain x coordinates. Mirror M2 has certain x coordinates, and we can calculate the change of the distance. This would be the change of these lengths d1 and d2. So for mirror 1, we have the following coordinates. So we choose our coordinate system in such a way that this is the x1 axis, this is the x2 axis, and the x3 axis then comes out of the board or goes into the board. Let's see, 1, 2, no, it comes out of the board then. So the x1 coordinate of this mirror would be d0, right? This is the unperturbed length of this arm. So d1 is a function of t. Yeah, if the gravitational wave comes in, these quantities will change over time. They are given by the square root of these distances. And well, if there's no gravitational wave, then the y's are the same as the x's. And we assume that the arm length in this equilibrium state is d0. And x2 and x3, of course, are 0. And for M2, we have x2 equal to d0, right? And x1 and x3 equal to 0. Okay, let's plug this in. Then we get, if I do this for the first mirror, I get here d1 of t squared. This is what? Okay. This is x1 squared plus x2 squared plus x3 squared. So this is dO squared plus 0 plus 0. And here I have the amplitude. X1 squared is d0 squared, x2 squared is 0, cosine omega t minus phi. By the way, of course, you could kill the phase just by shifting the 0 on your time axis, right? But anyway, doesn't matter. So this is just d0 squared. Here I get a 1 plus a plus cosine omega t minus phi. So, and analogously for d2. Here I have 0 plus d0 squared plus 0. Here I have again a plus. And this is now 0 minus d0 squared. So I have again d0 squared times something. This is 1 minus this time. Plus cosine omega t minus phi. Okay, so now we can calculate the phase difference, which then of course also becomes a function of t, because these two quantities change over time. This is the wavelength of the laser. This is of course not changing. So I get, or maybe, yeah, delta phi of t is then what? It is 2 pi over lambda 2 times, and then I have to take the square root out of these expressions. Square root of this is dO square root 1 plus a plus cosine omega t minus phi. And here's the same thing with a minus sign. Oops, minus dO square root 1 minus a plus cosine omega t minus phi. Well, of course, we don't expect very strong effects, so this amplitude usually is tiny. Yeah, it's a dimensionless quantity, it's a strain, so it's a relative change of distance. change of distance divided by distance. That's dimensionless. That's what we call the strain. And it's typically in the order of, well, if you are lucky, it's 10 to the minus 20 or something, not more than that. And so you can certainly expand this in the Taylor series, where you assume that this quantity is small in comparison to the one. And then we get delta phi of t is approximately what? 4 pi over lambda. 4 pi over lambda, d0. And if I expand the square root, I get 1 plus 1/2, yeah, from the Taylor expansion. 1 plus 1/2 a plus cosine omega t minus phi plus higher order terms, or I write them later. And then from the second term, I get minus 1 minus times minus gives plus again, plus 1/2 a plus cosine omega t minus phi, and then the higher order terms which are quadratic in a plus or of even higher order. So this goes away. 1/2 plus 1/2 gives 1. So this is 4 pi over lambda dO a plus cosine omega t minus phi. So that's the signal you get. Yeah, that's what the detector is really showing you. It shows you a phase difference, and it's given by this expression. And you see, it's totally different from what we had for these resonant bar detectors. For the resonant bar detectors, the dependence of omega was crucial. The amplitude was dependent on omega. Yeah, we had this resonance phenomenon that we got reasonable signals only if we were very close to the resonance frequency. Here, the amplitude is completely independent of omega. Yeah? Of course, the signal oscillates with the frequency omega of the waves. That's clear. But the amplitude is completely independent of omega. So this is a broadband detector. Yeah? In contrast to the resonant bar detectors, which are narrowband detectors. Well, on what does the amplitude depend? Of course, on A+, that's clear. Yeah, if you have a strong gravitational wave coming in, you get a strong signal. If a weak gravitational wave is coming in, you get a weak signal. That's clear. Then D0, that's most important. The longer the arm, the bigger the phase difference. And that's the reason why you don't do gravitational wave detectors with instruments which are standing in the lab on the table, but you do it with these things with arm lengths of 4 kilometers or something like that. So you want to have this big. But this is not the wavelength of the gravitational wave, it's the wavelength of the laser. Yeah, don't confuse these two things. They have nothing to do with each other. This has nothing to do with the incoming gravitational wave. It's just the laser wavelengths which you use for operating your instrument. Well, and actually you are not very flexible. For this type of instrument, you would work with something where this is close to the optical, just for technical reasons. So you cannot tamper very much with this here in terms of orders of magnitudes. So what you can influence and what you do influence is in particular this here, the D0. You make the arm length big. And well, the most important thing is that the amplitude is independent of omega. So that sounds marvelous. So you could detect all kinds of gravitational waves of any frequency which you get, which is coming in. You could detect them with these kind of detectors. Sounds great. Well, it's not quite so great, because of course you have to take the noise into account. And the noise, the sensitivity of your instrument depends very strongly on the omega actually. So what kind of noise would you have for this kind of interferometric detector here on Earth? Well, first of all, there are always small seismic perturbations. Yeah? With a GEO 600 instrument, it's near Hanover, which is not directly on the North Sea, but nonetheless you can very well measure the tides of the North Sea with this instrument. Yeah? So these tiny seismic perturbations can be very well detected with this kind of instrument. So that's one of the important sources for noise. How could you avoid this? Well, go away from the Earth, go into an orbit, yeah, consider a spaceborne gravitational wave detector, then you wouldn't have this problem with the seismic noise. And actually, this is planned. I will show you a few pictures in a minute of future instruments which might try to detect gravitational waves in an orbit. So seismic noise is one. Then, of course, thermal noise. All parts of your apparatus have a certain finite temperature. So the molecules are moving in a certain way, and of course this washes out the signal to a certain extent. So this produces noise. Thermal noise is the second thing, and here we have some. This is the same with the resonant bar detectors. Yeah, seismic noise and thermal noise was also an issue for the resonant bar detectors. And then, because here we are operating with laser light, we have something else which is very important. That's the so-called shot noise of the laser. Well, actually, when we do the theory, we do wave theory. We consider that the laser light is modeled in terms of a wave, of a continuous field. Actually, laser light consists of photons, and this produces. The very fact that actually I have discrete particles instead of this wave picture. This also produces a kind of noise, which is a matter of principle, which you can reduce to a certain extent, but never get rid of completely. So that's what one calls shot noise, Schrotrauschen in German. And it's one of the major achievements, in particular of the group in Hanover, to reduce these perturbing effects on the laser light as much as possible. So this was one of the major contributions from the group in Hanover. So they constructed the lasers, and they tested all the high technology for the lasers in Hanover, and then it's implemented in the bigger detectors like LIGO and Virgo. So in particular, they started a couple of years ago in Hanover working with what is called squeezed light. You remember the uncertainty relation? You have whatever you have for all kinds of particles, you cannot measure position and momentum simultaneously with arbitrary accuracy. As a product, delta x times delta p is limited. But you don't have a limit for the individual factors. And what is called squeezed light is light where you make one of these factors as small as possible. Of course, the price you have to pay is that the other factor will become big. And what you do is you make the delta x as small as possible. And then the delta p spreads. So in phase space, where you have an x-axis and a p-axis, the distribution would be squeezed in the p direction. Yeah, that's why it's called squeezed light. And this it's a fairly new and modern technology. They were testing this in Hanover, worked very fine. And in the next runs for the big detectors for LIGO, they will implement this squeezed light in the bigger detectors. At the moment, it's not yet. So LIGO is not yet working with squeezed light, but it will in the future. So these are the kinds of problem you have to deal with. You have to reduce the noise, all kinds of noises. Yeah. And when one of these detectors is upgraded, so you read in the news for a couple of months or even for a couple of years, they are shut down and they are upgraded, you may ask yourself, what are they doing? Do they make the arms longer or something like that? No, that's not what they are doing. They are doing two things. First of all, they raise the laser power. Yeah, that's an important thing. To introduce all kinds of tricks so that the laser power is raised. And the other one, the more important one, is they reduce the noise. Yeah, they introduce all kinds of tricks to reduce the noise. So that's what they are doing when they are upgrading these instruments. So the noise level is then reduced, and this is what what makes the probability of actually detecting a signal then bigger. Okay, that's the basic idea. So what you should keep in mind, in particular, the difference between the two types of detectors. One is a resonant detector, very narrow-banded, and the other one is a broadband detector, working over a fairly large range of frequencies, but of course also restricted by noise. Okay, now again I will show you a few pictures of the existing and planned interferometric detectors. Okay, so here's again the the basic setup of a Michelson interferometer. Actually, here's one additional thing shown, which I didn't show in this very simple sketch I've drawn on the board. I didn't have these two mirrors here. Actually, what are they good for? They are, the idea is that you have which I should take something like a pointer. You have the light beam going back and forth several times between these two mirrors and also between these two mirrors before they go to the detector, which is here. The idea is, of course, that you make the arm length longer in this way. Yeah? So you have to distinguish the geometric arm length, which is 600 meters in the case of GEO 600. It is 4 kilometers in the case of the LIGO detectors. You have to distinguish this from the effective arm length. And the effective arm length is much higher than the geometric arm length because it is multiplied by the factor of how many times the light beams go back and forth between the two mirrors. So in the case of GEO 600, this is only a factor of 2. Yeah, the light goes just twice between these two mirrors. So the effective arm length is 1,200 meters of GEO 600. In the case of LIGO, this factor is, I think, 400 or something like that. So they have, well, this is here shown in a very sketchy way. These are actually Fabry-Perot cavities. So these are cavities where the beam goes back and forth very often. And in this way, the effective arm length of LIGO is something like 400 times 4 kilometers, 1,600 kilometers. Yeah? Not meters. In the case of GEO 600, it's 1,200 meters. Here it's 1,600 kilometers. Yeah? So you have a very, very large effective arm length. And for Virgo, it's similar, I think. Virgo has an effective geometric arm length of 3 kilometers. And the effective arm length is also more than 1,000 kilometers, I think. So that's one additional thing. And the other additional thing is that, well, you don't just switch on your laser and let the light go into the instrument. You have a very sophisticated technique to raise the laser power. So they do what is called power recycling. So in the case of GEO 600, I think the laser is operating, so the output power is originally something like 10 watts, not more than 10 watts. But with these power recycling techniques, they make it possible that the beam is within when it is reflected between the two arms, that then actually the laser power is something like 10 kilowatts. Yeah? So this is another important issue to raise the laser power. So that's the basic idea. And here are a few of the instruments. So let's begin with our instrument here in Germany, which is not far from here, a few kilometers south of Hanover. It is called GEO 600. So the 600 it stands for the arm length. It's 600 meters. So here you see one arm. There you see the other arm. And here in this rather unconspicuous hut, you have all the technology. So there is a beam splitter, the laser, and all the other instruments. Of course, the tubes have to be evacuated, yeah, because the laser beam is traveling in the vacuum out to the mirror and then back. And what you have inside this hut is all the technology. Of course, this also must be in vacuum containers. So here you see, I think this is a beam splitter. I think the beam splitter is in this container. Here you see one of the tubes coming out. Yeah, and then it leaves the building and goes to the mirror. And here you have these other containers, which are housing these secondary mirrors and the system where the laser light is coming in. I think this is the apparatus where they produce the squeezed light, if I remember correctly. So the squeezed light is fed into the system in this way. And in the next picture, we can look inside one of these containers. So this is the beam splitter. Here's a beam splitter. Here's a laser beam coming in. And here's a squeezed light coming from another direction, and then it goes through the beam splitter. Actually, the laser beam is not visible, the one which they are using at GEO 600. I said already it's at 1,064 nanometers. This is in the infrared, so you cannot see it with your eyes. They made it visible here just for the sake of producing a picture where you can see how the light is moving. Yes, so this is how it looks inside this container, one of these containers, and this is one of the two LIGO detectors. So one of the two big detectors where actually the gravitational wave signal was detected in September 2015. This is the one in Hanford in Washington State. So the arm length, the geometric arm length in this case is 4 kilometers. And actually in this case, the Hanford detector, they have inside the same tubes, they have a second interferometer with an arm length of 2 kilometers. So these are actually two interferometers in one side. And again, here you have, in this building, you have all the technology. So the laser light is produced there, is then sent out, and the beam splitter is inside this building, and the detector is also inside this building. So this is one of the two detectors. The one in Hanford in Washington, and the other one is in Livingston in Louisiana. You can easily distinguish them if you see a picture. If there's forest around, then it's the one in Livingston, because this is in the swamps of Louisiana. And if the neighborhood is very dry and no trees whatsoever, then that's the Hanford side. Yeah? So they can easily be distinguished. Actually, they are not very far apart. Yeah, you know the size of the United States. Yeah, it's a few hundred kilometers. Yeah. So of course it would be better to have them on different continents. So then you could locate the sources very much better if you had a long baseline. So with these detectors comparatively close together, you cannot locate sources in the sky very well. So these are these two big instruments which are in operation since 2000 or 2001 or so. I already mentioned that they were upgraded for a while, then switched on again in summer 2015, and in one of the very first runs they found a gravitational wave signal. And I will talk about this signal in detail next week. Then there's Virgo, that's the other big detector. It's in northern Italy, not far from Pisa. This is the geometric arm length in this case is 3 kilometers, so it's not much smaller than the LIGO detectors. And at the moment it undergoes an upgrade. I think it's supposed to be switched on again this year, 2017. So then we have the big LIGO detectors in the United States and this big detector in Europe. Then we have already 3 detectors distributed over comparatively big basis, and then we could locate sources in the sky already much better than just with the LIGO detectors alone. Yeah, so this is something which will come up probably soon, and then GEO 600 will undergo an upgrade. GEO 600 was in operation during the time when the bigger ones were upgraded. They will then do an upgrade with GEO 600. It's then supposed to be called GEO HF. Don't ask me what HF stands for, but it will be an upgraded version of GEO 600. But as I said already, GEO 600 is not so much designed for actually detecting gravitational waves. It's more designed for testing technologies for the bigger ones. And actually, GEO 600 is a very important player in this game. So also the people from the other, who are working with the other detectors, they always acknowledge the big contributions that come from the German team, which provides in particular the laser technology. Okay, so these are the things which are existing already. Then there is one which will come into existence soon, or go into operation soon. This is now called CAGRA. It was originally called LCGT. I don't remember what this acronym stands for, but I do remember what the C stands for. The C stands for cryogenic. Yeah? So all the detectors I've shown you before, these first generation detectors, they are operating at room temperature. And now the idea is to do this at low temperatures, of course, to reduce the thermal noise. Yeah, that's the idea. So Kagra is in some kind of mine in Japan. I think it's very close to the site, or even on the same site where these famous neutrino experiments have been done, where they found that neutrinos have masses. So this is, as you see, under construction. Yes, this is a picture where from the time when the construction was going on, and it is still going on. I think Kagra is supposed to become operational next year, 2018. That was the plan. I'm not sure if they will manage to do this. You know, these big projects, they are always shifted to the future. Kagra also has an arm length of 3 kilometers, if I'm not mistaken. And yeah, the difference in terms of technology, the difference with respect to the other detectors is that it will be the first one which is operating at cryogenic temperatures to reduce the thermal noise. There was a smaller detector in Japan. It was in operation until, I don't know, 10 years ago or so. It was called TAMA. It was a small one, even smaller than Geo 600. So this was also one where technology was tested, but this is now a detector where we could hope that this would be at the same could operate at the same level of sensitivity as, or maybe even better than LIGO. So if this also goes online, then we have 4 great detectors distributed over a reasonable portion of the Earth. And then we could really investigate the sources in much more detail than with just the 2 LIGO detectors. So this does not yet exist, so it's not yet operational, but it will be operational probably very soon. More to the future is this thing, which is called the Einstein telescope. This will also be a cryogenic instrument. It's supposed to be underground. So it will be 100 or even 200 meters under the surface of the Earth. Also be operated at cryogenic temperatures. And so the idea is then to, again, to reduce the noise even further in comparison to present-day instruments. If and when the Einstein telescope will actually be built is an open question. So I think there are 8 European countries involved in this. So Germany is one of the players. The Albert Einstein Institute is one of the institutes which is involved in the Einstein telescope. Some other European countries, and but when and where this will ever be built is an open question. So these are the ground-based detectors which already exist or will exist soon or are planned for the foreseeable future. I think I will not live long enough to see the Einstein telescope actually work. And then we are, maybe first I should show you this picture of the sensitivities. So we talked about, you see, this is the strain, and when we do this Fourier expansion and we construct the power spectral density, then we get the quantity with this funny unit 1 over square root of hertz, you remember. Yeah, this is the thing which is again plotted here. It's plotted over the frequency. So for each instrument you have a curve here, and if a signal is received which is above the curve, then it's fine, then it can be seen. If it is below the curve, then it's drowned in the noise, and you couldn't see it. Let's look at this green thing up there. This is Auriga. This is the most sophisticated resonant bar detector which was ever built. It's now shut down, but it was in operation for a couple of years in Italy. And you see this is a very small frequency band, near 1 kilohertz. And the sensitivity, what is this? It's 10 to the minus 21, 1 over square root of hertz. So also you see the sensitivity is considerably smaller than that of the other instruments. All the other instruments are interferometric detectors. And from this picture you understand why the interferometric detectors are thought to be much more important for the future than the resonant bar detectors. So what do we have here? Here we have LIGO, the original LIGO and the original Virgo. Then we have advanced Virgo, which will start probably this year or early next year. And we have advanced LIGO. That's the two detectors which actually found gravitational wave signals. And you see they are considerably, they have a considerably broader frequency range in which they can operate. So they cover the area around 1 kilohertz where the resonant bar detectors work, but they are able to detect signals of higher frequency and in particular also of lower frequency. Actually 1 kilohertz is a fairly high frequency here for a gravitational wave signal. We already talked about this. So you need something which really contains frequencies of 1 kilohertz, so it must be a very rapidly operating source. So maybe a neutron star, a bumpy neutron star would produce frequencies in this range. And the only other source one could think of are burst sources, yeah, where you have bursts, where you have also contributions to the frequency in this range. All the other things, in-spiraling black holes or something like that, stellar black holes or supermassive black holes, have lower frequencies. So you want to push this a little bit more to the left, this picture. So here's, as I said, advanced. So this is a state of the art. Yeah, advanced LIGO exists. It is in operation. LIGO will be upgraded even further in the future. Here we have LCGT. That's what nowadays called CAGRA. So you see it would be more or less competitive with advanced LIGO. Going a little bit further down in frequency. And then we have this future project, the Einstein telescope, which of course would then be the best of all these instruments. So it would go down to, well, let's see, even the Einstein telescope wouldn't reach frequencies bigger than 1 hertz. And that's about the limit, as a matter of principle, the limit for earthbound telescopes. Yeah, for ground-based interferometric detectors. Yeah.
Warum sind da denn diese Ausschläge drin bei dem Einstellteleskop?
Okay, the question was where these spikes are coming from. Probably some resonant effects. I don't know exactly what's the reason for this. Okay, but they are fairly narrow banded, so fortunately we wouldn't get just a signal here at this particular frequency. Okay, what was I saying? Yeah, 1 hertz. So this is something maybe you could keep in your mind, that about 1 hertz is a limit for ground-based detectors. So we cannot go beyond this. And actually we do expect gravitational wave signals of lower frequencies. Yeah. In-spiraling supermassive black holes, they would have frequencies which are smaller than 1 hertz. So one wants to go beyond this limits, and that's one of the reasons why one started thinking about space-based instruments. The plan for such a space-based interferometer is old. It began already in the 1990s. The original name was LISA, Laser Interferometric Space Antenna. And the idea was to have 3 satellites. Yeah, these are 3 satellites. And a laser beam is sent from this to the other one, and from this to this one. And also, the original plan was also to have it between the two daughter spacecraft, and to have a Michelson interferometer operating in this way. Of course, there's nothing material between these satellites. Yeah, so the laser beams are just traveling through vacuum. And the original idea was to have an arm length of 5 million kilometers. 5 million kilometers, that's about 12 times the distance from the Earth to the Moon. And then you have to face the following problem. If you send a laser beam over a distance of 5 kilometers, you have it reflected here, and you wait for something coming back here. You can wait as long as you like, you won't get anything, yeah? Because the laser beam will spread so strongly that virtually nothing will arrive back. It works with the Moon. The Moon is 400,000 kilometers away. So you know there are these retro reflectors placed on the Moon. So we send laser beams from the Earth to the Moon, and a very small portion, but a measurable portion of the photons actually comes back. Yeah, that's what we call lunar laser ranging. And this is done since many years routinely. So with the Apollo missions, these retroreflectors were brought to the Moon. And with the help of this method, we can measure the distance between the Earth and the Moon, I think, to within an accuracy of a few centimeters, 2 centimeters or so. Yeah? So over 400,000 kilometers it works, but over 5 million kilometers it won't work. Yeah? So that's the reason why actually you don't have just the laser beam reflected. The idea was to have a transponder here, which when the beam arrives, which produces a beam, which is then sent back with a controlled frequency, so that actually it doesn't work with mirrors. It works with a kind of transponder where a new beam is produced in the in these other spacecraft. So the orbit was supposed to be something like that. So the Earth is going around the Sun, and this system of 3 spacecraft, LISA, is supposed to follow the Earth at a distance of 20 degrees. So it's also in an orbit around the Sun, and the system is kind of rolling on this orbit. Yeah, and the celestial mechanics is fairly complicated. I just had a couple of years ago. I had a look at the way in which this instrument is supposed to move. Of course, you want to have the distances as stable as possible. It's very tricky. By the way, it has nothing to do with the Lagrange points. Yeah, the Lagrange points are not at 20 degrees trailing the Earth. So this is a different idea of celestial mechanics, which is behind the construction. So this was this is a wrong heading here. This is the one for the next picture. Sorry. So this is the orbit of LISA, what we see here. So the original plan, I said already, arm length of 5 million kilometers, and that was the geometry. And then, as always, there were problems with financing. It started as a joint program of NASA and ESA. And then, NASA withdraw because they had other priorities, and for a couple of years it was very questionable whether LISA would start at all. So they scaled it down. So there was a plan to have it only with an arm length of 1 million kilometers, and also the third arm, the arm between the 2 daughter spacecraft, was cancelled. So then it became a little bit cheaper. And for a while it was called LISA, Evolved LISA, and then it was called NGO. Don't ask me what NGO was standing for. And but now, since gravitational waves have been detected with these Earthbound detectors, of course this gave an enormous boost also to this project. And we can now hope that LISA might fly in a fashion similar to the original plan, maybe around 2030. Yeah, that's the most optimistic expectation. So what would be the difference in comparison to the Earthbound detectors? An important difference would be the frequency range. Remember, the ground-based detectors, they were all above 1 Hertz. Yeah, they started here in this area. And now we could really reach the region below 1 Hertz. And also the sensitivities are very good, because you don't have the problem with the seismic noise. Yeah, the seismic noise is no problem for spaceborne instruments. So this doesn't exist yet. So we cannot. Nobody can show you real data, but these are simulated data. It's again the PSD stands for power spectral density. Yes, it's quantity measured in 1/root of Hertz. So that's what we expect for. We can now be optimistic that maybe LISA will be flying at some time. What we expect for LISA.
It's not so high, the sensitivity, right here. It was minus 23 even.
Yeah, it's lower. That's true. Yes, but the frequency range is different. That's an important advantage. And well, if you there's hardly any overlap with, but okay, if you extend this, you can hope that you have maybe signals here in this range, which can be detected with the ground-based interferometers and with such a space-based interferometer. And then, of course, you have a big baseline for locating the source in the sky. Yeah, so this would also be an advantage of having one of these instruments in space. There was something which, so LISA doesn't exist yet. So it's future, something planned for the future, but what exists already is a project which is called LISA Pathfinder. It is just one spacecraft, not 3 spacecraft, just one. And it was designed for testing the technology for LISA. So everything is in one spacecraft for this instrument. And it was just meant for testing, the positioning of the test masses, the mirrors, right, and to see if one can reduce the drag. Yeah, if one can have these things really moving drag-free in space. So for this reason, there was this Pathfinder mission launched, I think, 1.5 years ago or so. So it's flying now. It's still operating now, and it's an incredible success. Yeah, everybody who's talking about LISA Pathfinder is enthusiastic about this. It works much better than they expected. Yeah, so with such a mission, you always set yourself some limits, what you want to reach, what kind of accuracy you want to reach, and LISA Pathfinder is operating much better than it was supposed to operate. So everybody is very happy. This gave an additional boost for the LISA project, so that now, as I said, we are quite optimistic that maybe LISA might fly around 2030 or something like that. So maybe I have live long enough to see it in orbit. So this was an overview. I think it was the last picture. Yes. So this was an overview of what exists already and what is planned for the near future. So these are the detectors in the strict sense of the word, where you really have something on Earth or in orbit, where if a gravitational wave comes in, something clicks, and then you say, aha, here was a gravitational wave. Next time I will add a few remarks on other ways of how gravitational waves could be detected, not with detectors in the strict sense, but more in an indirect way. So I will briefly mention these pulsar timing arrays, which may be used for detecting gravitational waves. And I will briefly mention the idea of detecting gravitational waves in the cosmic background radiation. This was something which made headlines a couple of years ago when the BICEP2 collaboration announced that they had actually found a signature of gravitational waves in the cosmic background radiation. But it turned out to be an error. So this will be a short last part of this section, which I do on Monday. And then I will talk in more detail about the signals which actually have been observed and what we have observed in 2015 and 16. So that's the plan for the near future. And then we go back to theory for the rest of the term. Okay, have a nice weekend.